Welcome to the UVU CS3060 Lecture 2.5, where I discuss development and administration tools for operating systems. So, frequently, when you're writing a program, you have problems. There are errors. You need to see what a variable is set to. These tasks are debugging tasks where we go and with the realization there is a bug in our code, we investigate how the data is set up, and this task is called debugging. You've very likely done this with previous assignments. Well, you need to do the same thing with operating systems when you're developing an operating system. So this is done many different ways. Probably the most common way is actually to perform debugging by viewing the operating system logs that are created. There are actually lots of different logs. A simple one that everybody has access to, you can actually take a look at how the operating system started up. There's a program called dmesg, D-M-E-S-G. And if you look at the output of this dmesg, it actually shows you from the very start, second 0 of when the kernel was loaded, how this kernel operates. It shows you parameters for the kernel. It shows you device initialization. It shows you security fixes. It shows you interrupt setup. It shows you device memory handling. All of this. And you can see, even to this point, I'm at second 2 at this point, and it's still giving me information about how the operating system started up. Now, this looks like, and here's the end of the log. The system, the Linux kernel, was actually loaded in 10 seconds. All of the things were initialized, everything was ready within that time. Dmesg shows everything the kernel logged as it was starting up. And if you're creating a driver, you will likely add to this. You will add kernel log details that you can trace and make sure everything looks the way you hope it does. Now, sometimes a kernel log isn't enough. Sometimes you need more information. Well, another option is to gather information from a kernel that has died. You will frequently have, and this is similar. This is actually describing the similarity between an application crash. When an application dies, it can generate something called a core dump. And a core dump you view by looking at through a debugger. Well, an operating system kernel is just application 0. It's the first thing that's loaded on your computer. And if the operating system dies, you can get a crash dump from that contains all the data that was in kernel memory when the kernel died. And just like with an application core dump, you can use a debugger to view an OS crash dump. Now, beyond just debugging actual bugs and crashes, you can use something called trace listing, which we've seen a little bit of that when we use the strace program. You can also do profiling, and profiling shows what functionality is running and how long it takes to finish that functionality. And if you find a particular piece of functionality that is running slow, there's where you probably want to do some debugging. So this quote here, debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are by definition not smart enough to debug it. The upshot of this rule, and what you should learn from it, is don't be complicated. Write your code as easily readable as you can. When it comes to operating system code, simplicity is treasured above all others. If you write a complicated and very difficult to read kernel module for the Linux kernel, it will generally be rejected and you will have to go back and rewrite it. We have to have ways of checking performance. There are tools for doing that. Here is the Windows Task Manager that allows us to see if the operating system is functioning optimally or if there may be something that's causing problems. This is a very, very powerful tool for helping find programs that are taking more resources than they need. A similar program on Linux is called the top program. If you run top, it shows you your programs that are currently running on the operating system and lets you evaluate if one of them may be taking up too many resources. The Solaris operating system has a tool called dtrace. That what it does is it actually puts into the operating system code marks that let you see what's happening within a particular program, how things are operating. This isn't just debugging at the user space level, it is also debugging at the kernel level. So if you make a kernel call, it traces what functionality. Now, Linux has similar kind of things, but they're usually very difficult to actually work with. So these probes will actually indicate who's calling something and what the caller is doing. So here's another instance of how much time was spent in each particular section. So most of the time for this sked.d is actually being spent inside the Java module. And you can see that it's broken down into other, like screensaver, Metacity. All of these are shown as things that are happening within the scheduler, how much time the scheduler is spending in certain areas. One thing that is important when it comes to operating system tools, some operating systems require you to generate the operating system for a specific piece of hardware. The old NetWare operating system, back in its pre-version 3.0 days, had a sysgen program. And what it would do is it would check out the hardware, figure out which drivers were necessary, build those drivers into the kernel, and then provide a monolithic kernel. And sysgen can be similar to actually building your own Linux kernel yourself. Rather than going through a generic kernel that has lots of modules that it can load, all the module detection that goes on and whatnot, you can actually build a Linux kernel that has all of your specific drivers built into it. And then when that kernel boots up, it doesn't have to load a module. It's already there and it's ready to be initialized. This would be considered a system-tuned kernel. And it is not uncommon to have highly optimized systems have custom-built kernels, especially whenever it comes to high-performance kernels. Now, one last thing we have to discuss when it comes to tools of an operating system, when it comes to the kernel, is how a system is booted. There are usually several tools that accompany an operating system kernel to get that kernel into memory. It starts with the machine being turned on, and the machine will have what is called a firmware. This firmware holds some initial boot code, and it's usually very small. It usually looks at a very specific location for another program that it can load to continue getting the operating system up. So there's usually, after the firmware ROM will usually look for a bootstrap loader. And this bootstrap loader, which is in the firmware, will then go to a boot block. This boot block actually contains a small amount of code, usually more than the bootstrap loader, but it will contain a small amount of code that knows the operating system that it's trying to load and knows where to find the kernel. This is not something usually built into a bootstrap loader. So one of the common ones that we see is the grub bootstrap loader and boot block. The grub system isn't necessarily a kernel. It is just simply a small program that allows you to choose from a list multiple different systems, different kernels. This allows for a system where you can do what is called multi-booting. Now, once you've selected a particular kernel to be loaded, then that's the only system that's loaded for the duration of that kernel's run. You can reboot the system and go through this process again, where the bootstrap loader goes through the boot block and then finds the operating system kernel. Grub is common for Linux. Windows has its own bootstrap that tries to find the Windows NT kernel and get it up and running. And frequently there's competition between these two bootloaders to, if you install one bootloader and then try to install a second operating system with a different bootloader, it will overwrite the first one and cause problems. A good installer will be a good citizen, be a good neighbor, and try to install a multi-boot system. But some operating system installs just aren't good neighbors. This ends the UVU CS3060 Lecture 2.5, where I talk about tools and debugging methods of operating systems.